All right, so I'm back at the Glen Sebastian Nature Trail yet again, and the purpose of this week's lab, which will actually spill over into next week, is that we are going to be looking at water quality, in particular groundwater quality. Now, you may recall from our very first lecture that groundwater is the most abundant source of fresh water on the planet. So it's a particularly important resource for us. Now, one thing about groundwater as a resource is that if groundwater ever becomes contaminated, which it does from time to time, it's moving at such a slow velocity that it's going to take a long time for that contamination to work its way out of an aquifer. You guys are calculating groundwater velocity right now, and you could certainly notice that groundwater velocity is much, much slower than surface water velocity. Not only that, but groundwater is susceptible to picking up contamination from the land surface because remember, groundwater is replenished by precipitation, reaches the surface, infiltrates into the vadose zone, and then recharges to the zone of saturation. So let's say that I spill some chemicals here on the land. Well, it's highly likely that those chemicals will be brought with the infiltrating water down into your aquifer and thus contaminating that aquifer. So you guys are now working with contaminants, and I'll go into more detail about it in probably another video, but you're going to be working in groups for this lab, and each group has been assigned a contaminant. And so you guys will have to figure out how to remove that contaminant from the aquifer. So it could be an organic compound like benzene. It could be some sort of toxic metal like hexavalent chromium, okay? Well, one of the things that may help you with your remediation is to understand the geochemistry of the aquifer. In other words, if we understand perhaps the pH, or maybe we understand something about the amount of oxygen, dissolved oxygen, or maybe the redox, which are all things that I'll talk about in the lecture, then we might be able to understand the fate of our particular contaminant. So just to give you an example, benzene, for instance, is something that's inside of gasoline. It's also highly carcinogenic. So we worry about benzene and groundwater contamination when underground gasoline storage tanks leak and they release that gasoline and the benzene within into groundwater. Well, benzene is in gasoline and it's added as a fuel additive to increase the octane rating. So in other words, it helps your gasoline burn. So burning is a combustion reaction where you combine benzene and oxygen together and you get CO2 and energy. So if you can combine oxygen with benzene, it breaks down into CO2. In other words, you can do that by lighting the benzene on fire, which we're not going to do here in the ground. But there are also microorganisms that live in the aquifer that will basically eat the benzene. They bring in the benzene, they breathe in oxygen, and they turn that benzene into CO2, which is a harmless product. So that could be very useful for us if and only if we have oxygen in our aquifer. If we don't have oxygen, well, then we might not be able to break that benzene down. We might have to look at some other sort of remediation technique. So if we don't know anything about the aquifer, we may not know what our options are. So the purpose of this week's lab, or at least this portion of this week's lab, is to figure out what's going on in the aquifer, to figure out what we call the explanatory parameters that tell us about the geochemistry of the subsurface. So what I really have to do today is I just want to pull a sample and I want to do some simple analyses, okay? So I'm going to actually in a second here install this pump right here, this pump down here into MW2, and we'll pull the groundwater up to the surface. Now, a couple things that I want to say is that first and foremost, when we collect a sample from a groundwater well, it's important that we flush that well. We want to remove the stagnant water that's just kind of lingering inside of this well, and we want to draw in water that's coming from the aquifer. So we have to go through a process of what's called purging. So I'm going to let this pump run for a little while, and you may see, I don't know, it's been maybe 2 months or so since I've run this particular well. You may see that the water comes out kind of nasty looking. It may have some silt in it. It may have some oxidized iron and look kind of rusty. But after we go through the purging process, we're going to flush that well, that stagnant well water out, and we'll replace it with fresh water from the aquifer. This is just a really, really simple pump. I mean, it's about as simple as it gets. There's just a small turbine in the bottom of this, a little screen to keep sand from coming in. This is DC powered, so it's 12 volts. It hooks up to a car battery, and I've got some alligator clips over there. And on the other side, of course, I need my hose. Put these two together and drop this thing down. Now, while it's going down, I want to say that this is the ideal setup for a pump. Typically, we want to pump water upwards as opposed to trying to suck it up to the surface. There are pumps that will allow us to pull water to the surface, so we could leave the pump on the surface, in other words, and kind of suck the water up like you're sucking through a straw or something. But there's a limit to how high you can suck water before eventually the vacuum becomes so great that instead of pulling the water upwards, you actually start to boil it, which is something we want to avoid. Now, theoretically, that takes place at about 10 meters, so you can pull water up 10 meters over its surface, but in practice, it's going to be quite a bit less. And so we're not going to deal with that. We have to go down quite a bit. We got to go down, 8.4 feet to get to the water table, and when we start pumping, we're going to get a cone of depression, so this is the best way to do it. Okay. So I got my hose. Actually got way too much hose here, so I can pull this apart. It'll be nice and easy. Okay, so that's all set up. Getting our sample is all set up. So I've got my alligator clips here. Negative up first, positive. And here we go. Here comes the water. So maybe you'll see it in the video, I'm not entirely sure, but it's at first, right now coming through, got kind of a tannish color to it. There's a little bit of sediment in there, it appears to be. And it's already starting to clear up very quickly. So this well, it gets used often enough for hydro class. I'm pumping water through it quite frequently. That's going to keep that silt constantly flushed. Another thing that may happen in a well is if you let it sit, if you let it stay stagnant for some time, there's a high probability that you might get some sort of bacteria growing around your screen, and we call that a well skin. And the way to get rid of a well skin is just to pump your well. The problem is you may see that kind of orangish color come out towards the surface. It's almost like turning on a pipe for a bathtub. If you don't use it very often, it can come out looking kind of gross. Well, in the case of the well, it's going to have that iron precipitate. It's also going to a lot of times have some bacteria, this kind of film on the outside. But you just got to purge that well. If you have to purge for quite some time, if you haven't used a well in a while and you're picking up the bits of skin, then you go through a more sophisticated process called well development, which I've talked about before. So I can see that we're getting pretty good flow rate here. If I had to guess, this is maybe somewhere around, I don't know, maybe 2-3 gallons per minute. So just to be on the safe side, I'm gonna let this run for about 10 minutes. And then I'll know that I've purged for sure. Usually I'd have some way of measuring that volume, but you know what, I'm okay just to let it run for quite some time and be safe with it. One thing before I cut the video and cut ahead is that it's kind of cool. I can feel this water is cool. Feels nice and cool, maybe in the 50s or 60s. I'm getting a little bit of condensation on the hose here, so it's kind of nice. It's hot outside, but the groundwater is nice and cool because it's insulated. So groundwater tends to take on the average temperature, the average above ground temperature, if you get deep enough, that is. So we're still picking up probably recharge now that arrived maybe January, February, something like that, when it was a lot cooler. And as a result, the groundwater is nice and cool. So it's kind of refreshing. All right, so I'm gonna let this run for a little bit and then I'll be back to collect the sample. All right, so I'm back. It's been about 5 minutes or so. I'm ready to sample. I've purged my well, in other words. And so what I'm going to do is I'm just going to fill this thing up. I'm gonna let it overflow a little while. Basically, I don't want the water splashing in there because that's gonna bring up the oxygen concentration. So I'm gonna fill it up here, trying not to get my stuff wet. And I'm gonna stick this hose down in the bottom, and then you'll see I'm now gonna purge this bottle, in other words. And I'll let this overflow. And what I'm basically doing is I'm just trying to make sure there's no extra aeration or anything like that. Okay, now I can slowly pull the hose out. All right, and I want to make sure that there's like a nice bubble of water up on the top, because when I put this cap on, I want to try and have as few air bubbles as possible. So it's hard to do with the larger bottle, but I'm actually going to fill the cap up with water too. And I'm going to put these two together and seal it and try and get as few bubbles as possible. If I was sampling for something like benzene, we've talked about it before, or maybe trichloroethylene, those are volatile organic compounds, what we call VOCs. So if I put them inside of a bottle, a sampling bottle, and I had a big air bubble or something like that, it's possible that, and actually it's likely, that some of that benzene, some of that TCE, some of that VOC, in other words, will actually volatilize. It will evaporate from your water sample and enter into the bubbles. We call that headspace. So if you're sampling for volatile organics, which I'm not, you would want to have zero headspace. So no bubbles at all. And that can be kind of tricky and kind of fun. So I don't really have to worry about that. Now my sample's collected. I can see it's nice and cool. I don't want the properties to change very much as I transport it to the lab, which is about 2 or 3 minutes away. So I'm going to cut the video right here real quickly, and I will see you in the lab in just a second. We'll start analyzing this sample. Man, that's good.